For our second example recording, we're going to talk a little bit about vectors. Hopefully, again, a relatively quick and simple one. But what I won't do is do the graphic solution on this screen because I don't have a ruler and a protractor for very precise graphical solution. But for vector problems, what you can do, because a vector is a line whose length represents the strength or the magnitude of whatever the thing is that you're measuring, you can actually solve it geometrically, graphically. So on graph paper, with great care, draw a line 17 millimeters long and another line at 45 degrees south of west at 8 millimeters long, and then resolve from the origin of the first line to find it, and then actually measure the angle with a protractor and the line with a ruler. And you can get quite an accurate result. Your accuracy of your result depends obviously on how accurately you do the construction. So that's certainly one method, and the syllabus requires students to know both methods, graphical and algebraic methods of solving vector problems. So the algebraic method, I'm still going to draw a diagram. So there will be a vertical line. Oh man, can't draw straight lines with the stylus. Vertical line of 17, line at this angle of 8 millimeters in both cases, and then the resultant line. Can I draw dotted lines? Yes. Which is what we're actually looking for. We want both the magnitude and the direction, i.e. both the length and the angle of that to be able to fully describe it. So we'll use the cosine rule first and then the sine rule. So we need to remember a little bit of the algebra in non-right angled triangles. The trigonometry in non-right angled triangles. So the cosine rule is a squared equals b squared plus c squared, which is the good old Pythagoras for right angled triangles. But then for non-right angled triangles, we have to add in the factor minus 2bc cos a, where a is the angle that's opposite the side of length a. So in this case, we're finding length a, which is that dotted line, and the angle opposite it we know to be 45 degrees because it's the angle up in the top here, 45 degrees. So we can substitute in our values. The length of side B is 17 squared plus 8 squared minus 2 times 17 times 8 times cosine of 45. And if we work that through and do all the calculations with our calculator, I won't do them on the screen here, but it's relatively straightforward all the way through. We should get that the distance is 12.7 millimeters. Okay, and I've mentioned this before. We're wanting our students to be able to, when they do a calculation, immediately go, is that a reasonable answer? Does that make sense? In this case, it sort of does. It's 17 up there, it's 8 down there, so 12.7 as a fraction of that makes sense, I think. It's credible. If it was 127 millimeters we got added as our answer, we would know we'd gone wrong somewhere. It's the wrong scale. If it was 12.7 meters, we would know that there was something badly wrong. So in this case, that's actually fine. That's a sensible, plausible answer. Now we need to find the angle in here, which we'll just call theta. So for that, we're going to use the sine rule, which is a over sine A equals b over sine B. So we already know that A is going to... we're not using the same sides as A and B as we were before, in case that's unclear. Now we're going to use the 8 millimeter side as A, because that's the one opposite the angle that we care about, and we're going to use the 12.7 millimeter side as B. So if let's see, we should actually rearrange let's actually write it first. So 8 over sine theta, the angle that we don't know, is going to be 12.7 over sine. We already know that the angle opposite that is 45 degrees. So if we rearrange that, we'll end up with sine theta equals 8 sine 45. I've basically just flipped both sides and then rearranged, over 12.7. And if we calculate that out, and I should have actually calculated that out, we get a number, and then we need to take the inverse sine of the number that we get as the answer of that to find the value of theta. What students often do, and sometimes teachers do, is just put an equal sign there, and so they would have sine theta equals the final answer, which is 26.4 degrees. But as I once heard a teacher describe it, they're talking mathematical rubbish in that situation, because they've equated two things that aren't equal to each other. The equal sign has to mean something. So the equal sign means that whatever's to the left of it and whatever's to the right of it are equal. So if you just go on adding equal signs but then change what you're doing on one side, clearly, as that teacher said, you're talking mathematical rubbish. So just being aware of that and making your students aware of it. A bunch of this stuff that I'm saying, I'm sure you already know, but I'm emphasizing it because I want you to emphasize it for your students, because that's what actually helps them really understand what they're doing.